Hi everyone. As always, we start with the learning objectives, and you'll see that this time there's a lot of them. However, don't panic because most of this stuff is pretty easy. The only thing that's a little hard is refraction, and we did that last year. However, this year we will do this in a lot more depth, and there will be some deductions, and it won't be half as easy. But hopefully we'll get there. Alright, let's get started. So let's start with reflection, and we did this in the IGCSE, so this shouldn't take very long. Imagine that there's a surface, this surface here, where a ray of light shines in. And we want to know at what angle this thing is going to bounce back. Now pause the video and according to common sense and what we already did last year, tell me which angle this thing is going to bounce back at. Okay, hopefully you remember that the angle that this is going to bounce back at is exactly the same. So the angle of incidence, which is this angle here, and remember, when we talk about angles of incidence, it's never with here, with the surface, but with this line that's perpendicular to the surface. So the normal, remember that normal means perpendicular to the surface. So the angle of incidence is equal to the angle of refraction. If we do this, for example, for a certain object that's located here, now this object is going to emit light rays in all directions. So one of them is going to do this, and another one of them will do something like this, for example. And then if we've done things properly, then we can again use the law of reflection to see that this is going to bounce back at the same angle. Okay, that's not really the same angle, but you get my idea. And then we could project these lines this way and project this line this way, and it will look as if there was an object here. And this object, if we've done everything correctly, which I haven't because I have no pulse, you will see that this is just on the opposite side of the mirror. So this creates a virtual object on the other side. It looks like these rays are coming from here. And that's why when we look in the mirror, we see our mirror image. And now for our great friend refraction. Refraction is, remember from last year, is what happens when light goes from one medium, like air, into another medium, like water. And what happens is the light bends, and the reason for this is that the speed of light here is not the same as the speed of light here. And then you might ask yourself, how's that even possible? Like light should always travel at the same speed. So how come can it slow down here? And what's really happening is that photons, which are particles of light, are getting constantly absorbed and re-emitted by the particles in here, which causes an overall slowing of the light. So it's not really that light goes slower, but that it gets, on average, it goes slower because it gets absorbed and re-emitted by the particles here. Anyway, what we would like to do is calculate what happens when, like, if this is the angle of incidence, what is the angle of refraction given the speed of light here and the speed of light here. And in order to do this, we will need to define a quantity called the refraction index. And I'm sure you remember this from last year. N is the refraction index. And we define it as the relationship between the speed of light in vacuum. So let me just write that down. Speed of light in vacuum divided by the speed of light in the medium. So let's just take a moment to think about the possible values that n may have. Now, is there any possibility for light to be traveling faster than in vacuum? Pause the video and tell me. Okay. Now, the answer to this question is that no, it's impossible for light to travel any faster than in vacuum. So if it goes through water, it will slow down. If it goes through air, it will slow down a little bit, not much, but it will slow down. So whatever it goes through, it's going to slow down. Therefore, this number here is always going to be bigger than this number here. So n will always be bigger than 1. The only exception is if light is traveling through vacuum, or it's traveling, let's say, through air, where there's almost no difference with vacuum. In this case, this will be equal to 1. So the minimum value that n can have is 1. And otherwise, it will always be bigger than 1. Typical values of n are 1.3, 1.5, something like that. Now that we know this, what we're going to do is to use the fact that light has different speeds when it comes here and then refracts to deduce this relationship. So let's do that. Now first let me zoom out. And what we're going to do for this is we're going to use the wavefront approach. So instead of using the usual approach where we have rays, we're going to use wavefront. So here we have some water, or let's just say a medium. Just let's be super general, and I'm going to call this N2. And this medium here is N1. So these two mediums, they could be air, they could be water, they could be anything, but they have different speeds of light. And now I have a wave that's coming in at a certain angle until it hits this. And I'm going to use a pretty exaggerated angle so that things are easier to see. So the angle will be something like this. So these are my wavefronts. And there's a moment when this thing hits the surface. So right here, this part of the wavefront has hit this surface, but this part of the wavefront has not. So then I ask myself, well, what's going to happen? Well, if the speed of light here is smaller, let's imagine that it's smaller, then this is going to travel less than this. Therefore, the new wavefront will be tilted, which means that the new ray will also be tilted. And what I can do now is I can use trigonometry to find exactly how tilted this thing is going to be, and then I will derive Snell's law. So let's try to do this. Now, this is N1, so this means that light here travels at a certain speed. Let's just call it C1. C just means speed of the wave, so in this case it's the speed of light in this medium. And in this case, light travels at a speed C2. So then what I'm going to do is I'm going to look here and I'm going to assume that because this is a wavefront, the rays are perpendicular to the wavefront, so the ray is going to just keep going straight in this case. And this is going to be traveling for a certain time t. So in a time t, this is going to have gone c times t, right? So speed times time. So this will have a length of ct. And this t, I'm just making it whatever time. So the speed of light times the time, that's this length. And in this case, the same will happen. So this is going to go straight, but it's not going to travel ct. It's going to travel less. Actually, sorry, this should be c1t, yeah? It's going to travel c2t. So let's just draw that. So this guy is going to travel straight. This is going to be c2t. And therefore the new wavefront will be like this. Cool. And now what I need to see is that these two angles, this one and this one, are different. And I'm going to call this first angle, I'm going to call it theta 1. And I'm going to call this angle here theta 2. And you can see that there's two triangles here, they're two rectangular triangles, because this is a right angle. And they both share a side, which happens to be the hypotenuse, which is this thing. I'm going to call this L. And now we have pretty much everything we need. Now all I'm going to use here is just some basic trigonometry. I'm going to use the definition of sine for this triangle and for this triangle. So in this triangle, let's just find out how much the sine of theta 1 is. So sine of theta 1 equals what? Well, opposite over the hypotenuse, right? So c1t is the opposite side over L. c1t over L. And I can turn this around and you see later on why. I want the L to be on its own. So I'm going to say that L then equals c1t over sine of theta 1. And all I did was I put this over here and I put the sine over here. So I just swapped the L and the sine of theta 1. Okay, now I can do the same for the other triangle. So let's do the same for the other triangle, and I get that the sine of theta 2 equals, well, in this case it's opposite, is c2t, and the hypotenuse is still L. So I get c2t over L, and then I can do exactly the same thing that I did before and isolate L, and L will be just c2t over sine of theta 2. Okay, and now all I need to do is sum algebra. So let me just zoom this out a little bit. Let me leave this here. And I need to realize that these L's are the same one. So if this is equal to this, then this is equal to this. So all I need to do is to make this equal to this, and then everything will work out. So I have that c1t over sine of theta 1 has to equal this thing here, which is c2t over sine of theta 2. And then all I need to do is to swap this around. So I'm going to swap these two around and swap these two around, and also realize that there's a t here that I can just get rid of because it's multiplying both sides. So I'm just going to get rid of the t and then just swap these two things around. So then I'm going to get that sine theta 1 over c1 equals sine theta 2 over c2. And now I'm going to multiply everything by the speed of light in vacuum. So I'm going to multiply here and here by the speed of light in vacuum. So let me just add it up by hand. So c and c. And now all I need to realize is that c over c1 over c1, that's just n1. And c over c2, that's just n2. Because remember that the refraction index is the speed of light in vacuum divided by the speed of light in the medium. So then I'm going to get that n1 times the sine of theta 1 equals n2 times the sine of theta 2. And that is Snell's law. Do you remember that from last year? Well, now I deduced it for you. And I think you probably remember that last year I told you, in the IB I will deduce this for you, it's going to be a nightmare. Well, I hope it was not as much as a nightmare as I told you it would be, but I'm pretty sure it was. I'm not expecting you to be able to do this for yourselves, but I want you to realize that there is a reason for this. This does not just come out of the blue. This can be deduced by using some very simple principles, and then you get to this expression, which is Snell's law, and allows us to calculate the angle of incidence, so the angle of refraction if we have the angle of incidence. Now, just to recap and very briefly, I want to make sure that we're all on board with this. Here's Snell's law. Here's my surface. Here's my normal. Here's my incident ray, and here's my refracted ray. And I want you to pause the video and tell me where the angles are. Just point at them in the video. Where's the angle? Where's the angle of incidence? Where's theta 1 and where's theta 2? Okay. Hopefully you did this and you said that this is theta 1 and this is theta 2, not this and not this. Remember that theta 1 and theta 2 are always measured with respect to the normal. And you'll say, oh, but before, when we did the deduction, that's not what we had, because we had this. So what went wrong? Nothing went wrong. What happens is that here, we were measuring the angle with respect to the wavefront. So if I go back to here, and I make a wavefront that's perpendicular to my ray, you can see that this angle here is exactly the same as this angle here. So the relationships between the angle that we found out are the same as the relationships between these two angles. And if you don't believe me, I just challenge you to try it on your own and figure it out. Otherwise, I'll show you in class. But believe me, this angle and this angle are the same. Okay, so that was the hardest part. But now we need to go back to something that we did last year again, and that I also deduced for you last year, which is total internal reflection. And that's what happens when I'm coming from a certain medium of N2 into another medium of N1. And it turns out that N2 is actually bigger than N1. So if N2 is bigger than N1, what happens is, let's just draw a quick sketch. Now remember, N1 sine of theta 1 equals N2 sine of theta 2. And you need to remember that the sine is proportional to the angle, kind of. The idea is that the more angle, the more sine. So this means that if N1 is very small, then theta 1 will have to be bigger to compensate. Which means that when I go from a medium where N1 is smaller than N2, I should expect something like this. So imagine that I have this angle here, theta 1, and then I want to know whether theta 2 will be smaller or bigger than theta 1. And then I just look at this and I'm like, well, N2 is pretty small, so theta 1 will have to be pretty big. These two things have to be equal, so N2 is pretty big, therefore theta 1 will have to be pretty small, which means that theta 2 will have to be smaller than theta 1. And there's no problem. right? So I can make this as big as I want. There will always be a smaller angle through which there will be refraction. But what happens is if things go the other way around? What happens if I go from here to here? So let's zoom out and see what happens. So again, remember, n1 sine theta 1 equals n2 sine theta 2. And then again I have my surface. Here's still water. Here's my normal. And now this thing goes from here to there. So let's just, this is theta 1. And now in this case, I have that n1 is bigger than n2. So then I ask myself, okay, well, if n1 is bigger than n2, then theta 1 should be pretty small. And then n2 is smaller, so theta 2 can be pretty big, which means that this angle here should be bigger than this angle here. And you say, okay, so what? So this goes to a bigger angle. No problem, right? So this is smaller, and then this becomes bigger. But then I ask myself, what happens if I keep making this bigger and bigger and bigger? Well, this will keep getting bigger, but there will be a moment where this can't get any bigger, because it will be 90 degrees. And after that, that's not refraction anymore, that's reflection. If it goes back, then that's not refraction. So there seems to be a problem. There's a moment when this thing stops working. When this angle is big enough, this angle becomes 90 and this doesn't work anymore. Then refraction will stop happening. This is called the critical angle. The critical angle is what happens when this angle here, so this is the critical angle, when this angle is big enough so that this angle here is 90 degrees. Now it's really easy to deduce the formula for the critical angle, so let me just do that. All we need to do is take this. So first thing, n1 and n2, we don't know, but we know that theta 2 has to be 90, right? Because it's from that moment on, there's going to be no refraction because this can't get any bigger. So theta 2 is 90. So the first thing that I need to ask myself is, what is the sine of 90? So pause the video and tell me, what's the sine of 90? Hopefully you remember that the sine of 90 is 1. So sine of theta 1, sine of theta 2 is 1. So then I have that n1 sine of the critical angle equals n2 times 1, which is just n2. From here, I can just deduce that the sine of the critical angle is n2 over n1. That easy. Now realize that this will only happen if n2 is smaller than n1, because the sine can't be bigger than 1. So if n2 is bigger than n1, this will be bigger than 1, and then this will never happen, therefore there will be no critical angle. So the only possibility to have total internal reflection, which means that everything gets reflected, there is no refraction, is to have an n2 that's bigger than n1. Otherwise, no problem at all. So again, when I go from air to water, no problem. When I go from water to air, then yes, there's a problem. For a certain angle, light just gets reflected, there is no refraction. Now I'm going to go very, very quickly through diffraction because we did this in the IGCSE. Remember that normally, imagine that we have a wave like this, but a wave is really made of tiny wavelets that are all spherical. Okay, so each source of the wave acts as a point. So, sorry, each point of the wave acts as a source, not the other way around. And then when we add all these things, then we get a flat wave, right? And then this thing just keeps moving forward and forward and forward. Now what happens when I put a little aperture here? So imagine that I have a little door and I don't let most of the wave get through. So this will just go this way and most of this will crash against here. And then this thing here is going to just keep going this way. Well, since each point here acts as a source, I will have something like this. Okay? So what will happen is that the ones in the middle will keep producing something that's pretty much straight. However, here, there's nothing to keep this from bending. So there's not another point here that would create another little circular thing that would keep this straight, which means that the wave is going to bend and do something like this. So I'm going to draw this in white. It will do something like this, right? So what happens is that when a wave goes through an aperture, it bends. It does something like this, simply because the things in the middle don't have anything to keep them straight. So here, this guy was kept straight because there was another source here and another source here, so then all together made a straight line. Because these ones have been removed, then this thing just keeps being curved, so this just something like this. Yep. Now, this only happens though when this aperture is of comparable size to the size of the wave, so to the wavelength of the wave. If this does not, if this is too big, then we will not appreciate any effect. And the reason for this is, again, because we will have lots of tiny droplets, and then they will just make a line, and there will be really no reason for this thing to diffract. If this is very, very small, then this effect will be very, very noticeable. That's pretty much it. We did this last year. You know it from the IGCSE. When we do higher level, we will actually calculate things with this, and that's going to be hard. But for the moment, that's all you need to know. Now for something that we have not done in the IGCSE, and it's called interference. And this is what happens when two waves are next to each other. So here I have two identical waves, 1 and 2. And imagine that for whatever reason they end up in the same point. And we want to know what will happen at that point. Now, it's actually pretty easy to figure out what happens, and all we need is the superposition principle. And in case you don't remember, the superposition principle says that waves add up, which means that if I put these two things together, then the total pattern will be an addition of these two. That's pretty much it. So now we can ask ourselves this, well, okay, so what happens if I put them like this? So when they're just right next to each other, well, what will happen is then that I will get a pattern like this, right? The two waves will add up, and I will get a wave that has twice the intensity of, well, twice the amplitude of my previous one, because these two things are adding up. Good. But what happens if, instead of this, I take this thing, and they meet when this guy is here? Aha, well, then we'll have a problem, right? Because here we'll have 0, then this goes down, this goes up, so 0, 0, 0, 0, 0. So what we have is that if I have two identical waves that superpose in a certain way, like this, I get 0 amplitude. There's no wave there. We call this destructive interference. So before we had constructive interference, because together they make something bigger, and here we have destructive interference. Good. So now we're going to ask ourselves, okay, so when does constructive interference happen, and when does destructive interference happen? And it's all about the path difference, right? These two guys are at a certain distance from each other, and this distance is related to the wavelength. And we call this distance between them the path difference, because it's really a difference between how much path each of the waves has undergone. So imagine that these two guys come from the same source, but this guy has gone through 2 more meters than the other guy. Then the path difference is 2 meters. For example, we could have something like this. Let me just show you what I mean by this. Imagine I have a source here of waves. So here's my speaker that's emitting waves, and then I have something that will make waves bounce here. So one of the waves does this, boom, 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 then bounces off and goes here. And one of the waves does this. Now this wave has gone through more distance than this one. So the path difference is the difference in distances between here and here. And what will happen is that for certain path differences, I will have constructive interference, so I will hear a louder sound here. And for some certain path differences, I will have destructive interference, I will hear nothing here. And that's what I'm going to try to show you with the drawing before. Okay, so let's just erase this and go back there. Okay, so here I have my two waves, and I say, well, obviously I will have constructive interference when these guys are in the same position. Is there any other path difference that will also give me constructive interference? Pause the video and tell me. Well, of course there is. If I move this one wavelength, then I still have constructive interference. So it's either for 0 wavelengths, or 1 wavelength, or 2 wavelengths, and so on, and so on, and so on. So for anything that's a certain integer times a wavelength, I will have constructive interference, which means that for path difference of n, where n is an integer times lambda, I will get constructive interference. Simply because these two things add up. Okay, now when do I get destructive interference? Well, now all I need to do is say, okay, well, when these things are like that, right? And when these things are like that, what's the path difference? What's the difference between this guy and this guy? Well, it's, if this is one wavelength, this is half a wavelength. So, okay, so for half a wavelength, I have destructive interference. Are there any other options? Pause the video and try to figure this out yourself. Okay, well, yes, I can just move this a little further until here, for example, and then I will also have destructive interference. So how far am I? Well, this is one wavelength and a half, right? So it's 3/2 of a wavelength. So I have destructive interference for half a wavelength, for 3/2 of a wavelength, and I can just keep moving this, right? And in this case will be, whoops, so I will have 1, 2.5, so I will have 5/2 of a wavelength. So hopefully you start to see a pattern here, right? That for any non-integer number of halves of wavelength, any odd number of halves of wavelength, then I will have destructive interference. And we can express this more easily as n plus 1/2 times lambda. So for any integer n plus 1/2 times lambda, I will have destructive interference. This is the only thing you need to know to solve any interference problem. Now, a special case of interference is called double-slit interference. And when we do higher level, I will actually deduce this formula for you, but for now, I just want you to take, a very plausible explanation and then move on, because you're not required to know this in a lot of depth. The idea is that I have a certain source of wave here. This is like plane waves of a certain wavelength, lambda. And here I have this wall with two little slits, so that they act as point sources. So basically what I have is one wave coming from here and one wave coming from here. Now what will happen is that at each point in the wall, I'm going to have this guy having gone this long and this guy having gone this long. So there will be a path difference between this and this. And this is a path difference that I can calculate doing a bunch of simplifications and whatnot, and then you get a certain number. But the idea is that this path difference changes, right? So if I go to this point here, then this is shorter, this becomes longer, and so on. So for each point here, I have a different path difference. And for each path difference, I'm going to have a different amount of interference. So in some places, I will have destructive interference, then less and less destructive, then constructive, then destructive, and so on. So what I expect to see is something that alternates between constructive and destructive interference on the wall. So I expect to see something like this in an interference pattern. So something like constructive, because in the middle, both paths are the same, right? So this should be constructive, and then destructive, and then constructive, and so on, and so on, and so on. So this would be the intensity of light that I get on the wall. And it turns out that there's a formula to calculate the spacing between two consecutive maxima or two consecutive minima of this thing. So there's a formula to calculate this little distance here, which we're going to call S. So let's just call S. And I'm just going to give you the formula, and I'm not going to prove it to you. So S can be calculated as lambda d, big D, this one here, divided by d, little d, this one here. And that's all we need to know. Now this photo that appeared out of nowhere shows you what you get when you have two slits. So as you can see, it's not exactly what I told you, because apart from there being interference, there's also diffraction, and diffraction creates a different pattern that looks a little bit like this. So what we're looking at here is that this is really intense because this is the first diffraction minimum. So this little distance is here, this is this distance here. That's what you can see of the little double-slit pattern produced by one slit. And then what happens is that on top of this we have the pattern of the diffraction. And again, we will do this in higher level in a lot more depth, and I will deduce things for you and I will prove them for you. but this is right now at our level really hard, especially because we don't have enough practice with dealing with approximations and things like that, which we will do later on in the year. Alright, so finally we are at the end of the video. As I said, there was a lot of content, but just like in the other case, it's the problems do not reflect the amount of content. So I wouldn't panic too much. Here, what I really want you to take is Snell's law, critical angle, internal reflection, and then we need to understand the notion of path difference very well. Just the fact that if I have two waves, how much they've traveled, the difference in how much they've traveled is the path difference, and that depending on the path difference, there's constructive or destructive interference. The rest is much less important, especially since we're going to do this in higher level at a lot more depth. So now the rest is up to you. We need to do all the problem solving in class. I'll see you later and good luck.